We are now at question 5. The following diagram shows a ring X, and we can see the ring at X that is on a fixed pole AB, which is inclined at an angle of 40 degrees to the horizontal. So we are seeing all of that. Here's a pole AB, here's a ring X on AB, and AB is inclined at 40 degrees to the horizontal. The string, which passes over a smooth pulley P, is attached to the ring at one end and attached to an object Y at the other end. So here's a pulley system, here's the weight here's a Y, and we were told that Y is 15 kilograms. The coefficient of friction between the ring and the pole is 0.3, that's some mu is 0.3, and the ring is about to slip up the pole. So we are told that the ring is about to slip up the pole. So the ring is not yet moving, so we assume we have a limiting equilibrium situation here. So the object is in equilibrium since the ring is not moving, at least not yet. Let's look at the forces in place. So we're asked to label the diagram provided to show the forces acting on the ring. Before we go to the ring, let's look at what's happening at Y. At Y, we have a mass of 15 kilograms. So the weight at Y here, the weight is mg, of course, where m is a mass, so 15, and we are asked to use g to be 10, so it's 15 times 10. So the weight at Y here is 150 newtons. So this 150 newtons is hanging down. So opposite to that would be the equal force, since the system is in equilibrium. The tension, of course, this tension will be the same, 150 newtons, and the tension will be consistent right throughout the string everywhere. So this here we have also the tension 150 newtons. So you have 150 newtons pulling on the ring that's on the pole. But this 150 newtons is pulling on the ring at an angle to the pole, which means that this 150 newton will have two components, horizontal and vertical, so we need to resolve them. The horizontal is a component that would be parallel to the pole. By the way, this angle will be the same as this angle, since XP, the line string from XP, is parallel to the baseline here, so of course this will also be 40 degrees. So this component of the 150 that's parallel to the pole will be 150 cos 40, since we are resolving horizontally. This 150 will also have a component that's perpendicular to the pole, so resolve vertically. So the perpendicular force here for the 150 again will be 150 sine 40. So the 150 two components, 150 cos 40, 150 sine 40. Now, the ring itself, of course, has a mass, which means it will have a weight. So again, the weight of the ring will be acting perpendicular to the ground, and of course the weight is mg, and since this weight mg for the ring is at an angle to the pole, it will also have two components. So of course this angle will be the same 40 degrees, since this will be a right angle. So this angle will be 50, 90 minus 40, and this angle will be 90 minus 50, which is 40, so 50. So this again, the weight component, we need to resolve it two directions. Perpendicular to the pole would be mg cos 40, and parallel to the pole will be mg sine 40. So again, two components. Also, look at the situation here. The ring is about to slip up the pole, which means the ring is attempting to go up, which means friction will be always acting in the opposite direction. So friction also will be going down in this direction. So this direction will also have friction. And of course, it's static friction. Let me use fs to describe it, since the object is not really moving, at least not yet. So friction and mg sine 40 going down, 150 cos 40 going up parallel to the pole. And also, we'll also have a normal force, which is perpendicular to the incline, to the bar there, the normal force. Let me just use N to denote the normal force. And M will be the forces which are opposite, in the opposite direction, perpendicular. And there is two of them, one from the tension in the string, and that was 150 sine 40. And the other one in the opposite direction, perpendicular to the pole, is for the weight, from the weight of the ring, which is mg cos 40. So these seem to be all the forces acting on the ring. State one condition for the ring to be in equilibrium. So one condition is the sum of all the external forces must be equal to 0. And from Newton's second law, we know Newton's second law says the sum of all the forces, so the net force must be equal to ma according to Newton's second law. Now, the object is not moving, so there's no acceleration. So the net force, of course, is m times 0, which is 0. And of course, in this context, m would be the summation of the both masses. So we have an object at x, it's a ring, and we have an object at y. So in this case, m would represent the sum of both objects. So net force would be equal to 0. Next, determine the mass of the ring. Now, we know that the net force is equal to 0. The net force, let's denote it by that. F subscript net equal to 0. Let's find the net force. Let's find the forces in both directions now. So we're going to look at the forces which are acting parallel to the pole, attempting to go up. So we have, let me use going up for the positive and going down for the negative. So we have 150 cos 40. Let's pull in. So we have 150. We have 150 cos 40 going up from the tension there, and going down in the other direction will be friction and mg sine 40. So we're subtracting from that. These friction and the weight of the ring are resisting the motion of the 150 cos 40. So we subtract those, subtract friction and mg sine 40. So we subtract friction, static friction. We subtract also mg sine 40, and those should be equal to 0. Now let's calculate friction. Now friction, and the static friction, since it object ring is not moving, is mu times n, or of course mu is the coefficient of friction. So its friction is 0.3, that's the coefficient of friction, 0.3, times sine 150 sine 40, so that's 150 sine 40 plus mg, and of course g, we're using g to be 10, so it's plus 10m cos 40, so plus 10m, where m is the mass of the ring, cos 40. If we distribute the 3, the friction would be 0.3 times 150, that's 45. Sine 40, and if we multiply 0.3 by 10, that's 3m cos 40. So that's the expression for friction. 45 sine 40 plus 3m cos 40. So we can plug that into the equation down here. 45 sine 40 plus 3m cos 40. So friction there in the bracket, minus mg sine 40 equal to 0. So we can distribute. So what we have is 150 cos 40 minus 45 sine 40 minus 3m cos 40 minus mg sine 40. So we can leave all the terms with m on the left hand side. Well, equals 0. So we can, let's group all the m terms on the right hand side. So what we have is 150 cos 40 minus 45 sine 40. And we have two terms with m, 3m cos 40 plus mg sine 40. And now we can factor m on the right hand side. Factor m, right hand side we have 3 cos 40 plus mg sine 40. Now g is 10. So factor out m, we'll have with g sine 40. And g is 10. So that's 10 sine 40. Over here, we have 150 cos 40 minus 45 sine 40. So we can divide both sides by the bracket. We get 3 cos 40 plus 10 sine 40. Divide by the bracket here, same thing. We get 3 cos 40 plus 10 sine 40. So these terms cancel. So we're left with m equal to, on the right hand side, the left hand side, that's 150 cos 40 minus 45 sine 40. I'm getting 85.98. Divide 3 cos 40 plus 10 sine 40 equal 8.726. So m, which is the mass of the ring, is equal to 85.98 divided by 8.726, within 9.85, and of course it's kilogram. Determine the normal reaction of the rod and the ring. We have a formula for normal reaction n. Let's look at what we have again for n. We have an expression for n, 150 sine 40 plus mg cos 40. So 150 sine 40 plus mg cos 40. 150 sine 40 plus mg cos 40. So now we know the mass of the ring. So that's 150 sine 40 plus, we know the mass of the ring is 9.85. We know G is 10. So we'll substitute those. So the normal reaction, use your calculator to calculate that. So it's 150 sine 40 plus 9.85 times 10 times cos 40. And we're getting 171.87. And of course, part B, the following diagram shows a 3,500 kilogram automobile which travels down a 10 degrees inclined plane, inclined to the road at a speed of 20 meters per second. So our car driving down, initial speed, so initial speed here is traveling with U is 20 meters per second. If the driver jams on the brakes, causing his wheels to lock, and the coefficient of friction between the wheels and the road is 0.5, determine the deceleration of the automobile after the brakes are applied. So deceleration, another word for acceleration, so they use deceleration. When the brakes are applied, the car will slow down and start to skid. So because the speed, of course, we expect the speed to decrease, we refer to it as deceleration. So acceleration is when the speed is increasing, that's a positive value, and deceleration is when the speed is decreasing, still acceleration, but a negative value. So again, we need to determine the acceleration or deceleration. So first, so what will happen with car start to skid is that the component of this force, again, so always mg sine theta going down. Opposing that will be friction, and friction is always mu mg cos theta. So using Newton's second law, the net force is equal to mass times acceleration. So going down, when skidded, is mg sine theta, and opposing that is friction, and friction is mu mg cos theta equal to ma. So we can make some substitutions now. We know the mass of the car is 3,500. So 3,500 times g, which is 10, sine the angle 10 degrees, minus mu, coefficient of friction, that's 0.5. So minus 0.5 times 3,500 times 10, for g, cos the angle 10, equal ma, and m is 3,500. Times a. So substitute these values. We end up with negative 11, 156.45 equal to 3,500. We divide both sides by 3,500, so this is the net force. We divide both sides by 3,500 to solve for A. So we end up with A equal to, so we divide this by 3,500, negative 3.19. So with A to be negative 3.19. And we expect a negative value, deceleration, same as a negative acceleration. So the deceleration is 3.19. So deceleration is 3.19, but negative 3.19. So, and by the way, the units, don't forget the units, it's meters per second square, right? So, the unit, let's put in the unit, squeeze in the unit. Final thing is meters per second square. Meters per second square. Next, we're asked the distance the tires would skid on the road. So, we know that v square equal u square plus 2as, where v is the final velocity. So the car would skid to a stop. So the final velocity, v, that will be 0. The initial velocity was 20 meters per second. So u, initial velocity is 20, u square is 20 square, plus 2 times a, and we've just found a to be negative 3.19, so plus 2 times negative 3.19 times the distance s. So this will be 0 equal to 400, 20 times 20, 400, and 2 times negative 3.19, that is negative 6.38 s. So we can transpose, so this is bring this over, so we are positive 6.38 s equal to 400. Divide both sides by 6.38. So s is equal to 400 divide 6.38. That's 62.69. We'll call it 62.7. So distance will be 62.7 meters. Also calculate the loss in kinetic energy if the car moves a distance of 5 meters after the brakes are applied. So we know what the formula for change in kinetic energy. Change in KE is equal to net force times distance. So the net force, we have found the net force. Remember, the net force was, the net force here we have on the left hand side. The net force was this value, negative 111, negative 111, negative 11, 156.45. That's what all the left hand side record to be. Negative 11, 156.45. So negative 11, 156.45 times the distance of 5, and that works out to be 55,782.25 joules. And we expect it to be a negative value because kinetic energy was lost. Alright? So hence the change in KE is a negative value, indicating that KE was lost. Question 6. At a point P, a golfer hits a ball of mass 46 grams at an angle of 35 degrees to the horizontal. The golf ball travels in the air until it hits the ground at a point Q, which is 20 meters away from P. Just to do a representation of what's happening here. So here we have a flat, right? Well, show this better. So here we have a flat golf course, we're assuming. So here is P, here is Q, and the golfer hits the ball. So obviously it travels in the form of a trajectory. Alright, so the ball, of course, it was hit at an angle of 35 degrees with some initial speed. And the distance from P to Q is 20 meters, we are told. So the question asks us to determine the speed of the golf ball at P. So the speed is called the speed U, because it will be initial speed, U. So the speed. Now we know that the formula for a range is our horizontal range is v square sine 2 theta over g. And the range, we're given the range from P to Q, we're told it's 20. So 20, V, we don't know V, well, VU, we're using U, initial speed, right? So U square. So U square, sine, now theta is 35 degrees. So 2 theta is 2 times 35, so 2 theta is 70. We're using G to be 10. So we can just multiply across there, multiply both sides by 10. We end up with U square, cross multiply, we end up with U square or V square, whichever, it doesn't really matter. U square sine 70 equal 10 times 20, that's 200. So to find U square, we divide both sides by sine 70. So U square equal to 200 divided by sine 70, which means U square 200 divided by sine 70, that's 212.84. So therefore U will be square root of 212.84. So the U, that's initial velocity, is equal to square root of that, 14.6 meters per second. So initial velocity here, the ball travels at would be 14.6 meters per second. Next, we are asked to draw a label diagram to determine the position of the ball after 1 second. So notice the ball is hit, so we have two components, the vertical component and the horizontal component. So the vertical, let's do the horizontal component first. So the horizontal, that's the horizontal component. So the horizontal component would be so we know that distance equal to speed times time. So distance equal to speed times time. But the speed we're talking about remember the initial speed was 14.6 meters per second previously. So the speed, we're talking about the horizontal component of the speed. So that's mu cos theta times the time, and the time we're given is 1 second. T is 1. It's 1 second, right? So this is we're taking the horizontal component of the speed, so that's 14.6. That's the speed, and the horizontal component is cos 10 times 1. So 14.6 times, was it angle? So the angle was 35, not 10, so it's 35. So 14 cos 35. So 14.6 times cos 35, that will give us 11.96 meters. Let's now calculate the vertical component. We can use a formula S equal UT plus half at square. So s, but u this time now we're using the vertical component. So horizontal was u cos theta, the vertical would be u sin theta times t, and t is 1. So just u sin theta, and the value of t is 1, plus half and of course we're using acceleration, and of course it's going up, so negative, we're using actually negative g, gravitational acceleration, times t square. Now the t, this 1 second, so t is 1, so just half of a, and acting against gravity, so it's actually minus half, because g would be negative in the end. So this is, we substitute, so u, that's 14.6 sine the angle, which is 35, plus half, and we're using g, we're using negative 10 since it's going up, so we use g to be negative, since when going up it will be opposing, gravity will be opposing the upward motion of the golf ball. So this would be 3.37. So to show if it do a diagram now in terms of the coordinate, so this is a vertical component, by the way, so the vertical component. So in terms of a coordinate, the position would be 11.96 for the horizontal and 3.37 for the vertical. So let me do a quick sketch just to represent that. If I do a quick sketch, so of course, let's have a sort of a coordinate system. Sort of, so here's a golf ball, so y, x. So the golf ball is hit. It rises up, moving in the form of a projectile. So here to here, if this is P, this is Q, I've decided this will be 20. So let P be 0, 0, right here, let P be 0, 0 here. 11.96, so remember it was 20, so 11.96 will be somewhere past the middle, because at Q would be 20, this will be 20. So 11.96 will be somewhere here. Let's say 10 is somewhere here in the center. 11.96 meters would be just a bit past the 10. And then the vertical height, 3.37. So the ball would be, oh, that was just better. It should be on the motion of the ball, right? It's on the motion. So this is about here, 11.96. It's estimating 11.96, not drawn to scale, and the vertical would be 3.37, something like that. So 3.37, and we're using meters. So 11.96. So this is the ball moving from start to finish. Alright, so after 1 second, this is the position of the ball. Calculate the speed and direction of the ball just before it hits the ground. So again, look at a situation from P to Q. So P, Q. So I want this situation here, this speed and direction of the ball. So the ball will be somewhere here, just before it hits the ground. Now again, the speed will have two components. So we have the horizontal speed. It doesn't change. Change horizontally, there's no acceleration. So the horizontal speed, called the Vx, was 11.96 meters per second. The vertical speed, if using the formula, V equal U plus AT. So V Remember the initial speed was 14.6 meters per second at 35 degrees. So this would be 14.6, and we're taking the vertical component of the speed, right? So 14.6 and the vertical component sine 35. So remember the horizontal component cos 35, the vertical component sine 35 plus A, and it's rising. So for A we're using gravity, so it's rising against gravity, so we shall use -10. And then the time it takes to get from P to Q. Let's calculate the time it takes to get from P to Q, from P to Q. Now remember, let's do this part of the motion. Remember that V equal to U plus AT. So if we're taking the time between it leaves P to when it reaches maximum height, consider that time just alone. The V, initial V would be vertically would be 14.6 sine 35. Well, no, that's incorrect. If you're talking about when it reaches the maximum distance from P to the maximum height, at the maximum height it's 0. So we use it vertically, we use V to be 0 here. And of course U vertically would be 14.6 sine 30, remember the angle is 35 degrees, sine 35. And A with -10, since going up against gravity, so -10 times T. So we can transpose, which means that bring over the 10T, which means that 10T will be equal to 14.6 sine 35. Divide both sides by 10. So T would be equal to 14.6 sine 35 divided by 10. That's 0.8374 seconds. So to get from P to the highest point, which is midway, which is 0.374 seconds. Which means that the total time to get from P to Q, we just double that. So the total time, if I multiply, so this is T. To get from P to the highest point, and then from the highest point here to Q would also be the same T. So the full journey is actually 2T. So if I multiply both sides by 2T, and 0.8374 times 2, 1.675. So the full journey from P to Q is 1.675. So that's what we're using here for this time, 1.675. So from P to Q, we're using the formula V equal U plus AT. So V, so final velocity, initial vertical component of the speed, minus 10 times the time, the total time, that's 1.675. So let's write that better. There's minus 10 times 1.675. So this will give us 8.37 meters per second. That's the speed it will hit here. So if we to draw a little sketch to show the direction, this would be it. Let me just draw a little sketch. So this would be actually that's -8. So to do a little sketch, so vertically, the vertical component of the velocity, that's 11.96, and the horizontal vector, so the horizontal is 11.96, and the vertical, so V subscript Y, is negative, so its effect is going down. So this 8.37. So in terms of diagram, so it will hit like the ball will hit like that at an angle. So maybe we can calculate this angle. This is the angle it will hit the horizontal with. This angle is theta. This alternative, this angle is also theta. So to get this angle, we can use the tan ratio. So tan theta, tan is opposite over adjacent. So if tan opposite over adjacent, or the y component over the x component. So tan here, if you call this angle theta in the triangle, opposite is 8.37. Adjacent is 11.96. So if we calculate that, we get 0.7. So theta is tan inverse 0.7. So theta would be tan inverse 0.7. Theta would be 35 degrees. So the ball will hit the horizontal at an angle of 35 degrees. This angle will be the same angle as the angle it left the ground at. Part B. A golf ball collides with a stationary rock at point Q. After the impact, the golf ball rebounds with a speed of 3 meters per second, and the rock moves forward with a speed of 4 meters per second. Define each of the following terms. Impulse is can be defined as a change in the momentum of an object. And momentum can be defined. Momentum is an object mass times its velocity. So object is just a product of an object mass and velocity. State one assumption that must be made about the golf ball and the rock. So we say that one assumption is that momentum was conserved. In other words, the momentum before the collision is the same as the momentum after the collision. Determine the mass of the rock, so we can use the conservation of the principle of momentum. So let's look at the situation again. So a golf ball collides with the rock at a point Q after the impact. So I guess it's in context with the question we just looked at a while ago, where the golf ball at Q, where the golf ball was hit and it had Q. So it hit the ball, it hit the rock at Q. Alright, the ball hit the golf ball hit the rock at Q. So let's look at the situation now. And the golf ball had a mass of 46 grams. And the velocity, the velocity was, what was the velocity? 14.6, but we're taking of course we'll be taking the horizontal component. So we have the golf ball, so we have the rock. So before, let's do before and after. So before, we have the golf ball and we have the rock. After the collision, what will happen now is that the golf ball, let's look at what happens again. The golf ball rebounds with a speed of 3 meters per second. And the rock moves forward with a speed of 4 meters per second. So the golf ball, so the golf ball rebounds. So the golf ball rebounds with a speed of 3 meters per second. And the rock moves forward with a speed of, what's the rock speed? 4 meters per second. What else we know? The mass of the ball was 46 grams. So the mass of the ball was 46 grams, right? So we assume that didn't change. And the mass of the rock is what I want to find. Initially the rock was at rest. So the speed of the rock here was 0 meters per second. And the speed of the golf ball was, of course, we are using the horizontal speed. So V equal 11.96. This was the horizontal speed, or the horizontal component of the speed for the ball. So the principle of conservation says that momentum before equal momentum after. So the momentum before for the ball is mass times velocity. By the way, the mass, convert the mass to kilogram, we divide by 1,000. So the mass is 0.046 and the velocity is 11.96 plus the momentum for the rock. The mass, we don't know the mass, but we know the velocity is 0, so that will come to 0. Over here, the momentum for the rock is mv. M times V, we don't know the mass, we don't know the mass, let's call it M. So mv, mass times velocity, m times 4, that's 4m. And the momentum for the ball, mass times velocity, the velocity is going to the left, so we use -3. And the mass is 0.046. Change the value to kilograms, so we divide by 1,000. Again, so mv for the ball before the collision, m is 0.046, velocity 11.96. Here mv, v0 for the rock. Over here, after collision, the rock, m times 4, so 4m, mv, v is 4. Here for the ball, mv, remember momentum is equal to mv. So but v is in the opposite direction to the left, so hence -3. And the mass is 0.046 kilograms. So let's calculate for m. So 0.046. So let's calculate this. So this is 0.046 times 11.96. That's 0.55016 equal to 4m. And then 3 times 0.046. Well, 0.138. So we can transpose for 4m. Bring over that is 0.55016. Plus 0.138, and we are getting 0.68816. Divide both sides by 4. Divide both sides by 4. So m is equal to 0.17. 0.17, and of course in kilograms, so 0.17 kilograms.